Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection, of course. In particular, today you should take everything with a huge pinch of salt, because I'm going to waffle a little bit why I like polynomials much more than numbers. So in my opinion, numbers are complicated beasts, and I just can't work with numbers. And well, the so-called Mason-Stothers theorem that I'm going to explain today is kind of my main motivation, or a main motivation for me why I like polynomials so much. If you want to ignore that I like polynomials more than numbers, that's good. Don't worry, this theorem itself is still pretty awesome. And yeah, it will be a polynomial version of a very well-known conjecture or theorem in number theory, which in the end, my point will be, waffle aside here, that the polynomial version is just much easier, because in some sense polynomials are much easier. There are fewer coincidences within polynomials. Um, so the subtitle today is the ABC of polynomials, and yeah, we will see what that actually means uh, right now, because there will be an ABC version of a polynomial version of this ABC in number theory that we see right here. So ABC in number theory is one of the most important conjectures in kind of classical number theory, in the sense that it is honestly about numbers. So modern number theory doesn't really need to be about numbers anymore. Again, waffling. So take everything with a pinch of salt, as I said. Anyway, so it's a pretty simple statement. So you take three numbers, ABC. That's why it's called ABC conjecture, and A plus B equals C. And yeah, they're co-prime, so they don't share any common prime factors. And what you do is you take the radical, so-called radical of them. Um, Very easy definition, just the product of all distinct prime factors. Show you an example in a second. Just very easy to compute if you know the prime decompositions of ABC. Anyway, and the ABC conjecture, roughly speaking, states the following. So C is always smaller or equal than the radical of ABC. Nope, that was wrong. That would be the polynomial version. No, C is always smaller than a radical of ABC, but always is flanked with almost always. There's a precise way of making this almost precise. The point is there will be exceptions. And the ABC conjecture itself is more about the exceptions than about, well, this C being lower or equal than the radical. And those exceptions are pretty tricky uh, to find. There was one of the first worldwide running project with many people and those many computers involved. Link is in the description. I tried to find those exceptions for up to a certain bound, and there are quite a few of them, but compared to the bound, there are almost no such exceptions. An exception here is written down below, and it also helps us to understand what the conjecture is actually all about. Okay, so if you take those three numbers, don't look too much at the numbers, it's just A, B, C. A plus B is hopefully C, otherwise I've screwed up my numbers. And the point is, you would then look at the prime decompositions of those numbers. And I stole this actually from a nice Mathematica demonstration linked in the description, where I think in that demonstration you have 234 such funny triples. This is one of them. Anyway, so you look at the prime number decomposition, you write down the radical, which in this case is you cross out all the, it's just a product of distinct prime factors, so you cross out all the exponents. So it's 2 times 3 times 5 times 7 times whatever times 13. Apparently this is this number, and as you can see, this is much smaller actually than C itself. C is pretty huge, and this is one of the exceptions. This usually doesn't happen, and the way to measure this is given by this quality Q. It doesn't really matter how it is defined, everything is linked in the description anyway, but it really rarely happens that this is so skewed. So most of the time you would expect that this Q of ABC is smaller than 1, and very rarely you see it go above 1.4, and even rare do you see it go above 1.6. There are only a handful of examples, I think, where it's bigger than 1.6, even among those, well, a handful compared to 10 to the 18. Anyway, so this is one of the conjectures. And number theory is one of the most important ones. And it's, well, I don't want to judge anyone, but there is a proposed proof. I don't want to say anything about it. Some people believe it, some people don't believe it. That's what it is. But I think most people would agree that any proof of this statement will be just ridiculously complicated, or it's probably very, very, very complicated if the statement is even true. So we don't know whether it's true, strictly speaking, in some sense. A proof probably will be extremely complicated, and you definitely shouldn't try to prove this. I mean, no recommendation here to prove this. Certainly not. It will be too complicated, probably. And the problem is kind of that the counterexamples are kind of random a little bit, and it's not quite clear why they come up and why they just pop out of nowhere. Yeah, so problem is my statement star wants to be C is lower than or equal than the radical, but it's not quite. You have those funny counterexamples, and we don't really know what to do. The statement is also, which I haven't written down precisely, is also built such that finding counterexamples doesn't help to prove it, because it's kind of an asymptotic statement in some sense anyway. So one of the most famous, let me call it an open conjecture here in number theory. And the one that is even much more famous, and that's really a theorem, is Vermaslast theorem. That's extremely popular and was a huge breakthrough in the 90s. Not so much because the theorem itself is very exciting, but the biggest part was that there was very exciting mathematics going into it. And still, let me explain it. It's a very easy statement that I just want to formulate as follows. The Fermat curve, which is this one here, I've given you a few pictures here of how the Fermat curve looks like. The circle is probably the most well-known one. This is the n equals 2 case. The Fermat curve basically doesn't have any non-trivial rational points, unless n is 2. For the circle, you can find any kind of rational points. Let me illustrate that. So the classical example of Fermat is, for n equals 2, is this Pythagorean triple. And the only thing I did is I got rid of this one by just dividing it, such that I have a equals 1 on the other side, right? So that's why this is equivalent to the Vermaslast theorem, which you might have seen as x to the n plus y to the n equals z to the n. So I just divide by z to the n. Why not? So the statement is, well, okay, are there rational points? No, there aren't if n is bigger than 2. And this follows directly from the ABC conjecture. Link is in the description how this precisely works. But again, I mean, this theorem is famously difficult to prove. And as I said, that's nothing bad a priori, because you get lots of interesting mathematics on the way. So, but the polynomial version is just ridiculously much simpler, and again, polynomials are simpler than numbers in some sense, at least. Yeah, so I'm waffling a lot, I know, but anyway, let's move on to polynomials. And you do the same calculation. You have an A and a B and a C, and C is A plus B, right? So here's an example. You take A, you take B, you take C, and yeah, the way to find those triples is, I mean, polynomials are very rigid in some sense. Basically, take two random A and B's and add them together, you get a C. They will be almost sure they will be coprime. In this case, they are. So this is just C. So the calculation you need to do is exactly the same as before. So you get rid of the multiple factors. In this case, just this one dies. And this was supposed to be a 2. And this is this factor. The 2 doesn't matter anymore, because I want to count the degree anyway. So the thing you need to do now is, before you were just comparing numbers, and now you need to compare polynomials. How to compare polynomials? Well, it's not obviously clear, but a good way of doing it is just to look at the degree, the maximum power of x in my notation that you see. And in this case, the radical, let's do a count. It has a 1 here, it has a 1 here, it has a 1 here, and then it has 4 here. So the degree is actually 7, and C is, of course, of degree 4. So this is the equation. Degree of C is smaller or equal than the radical of ABC, but put a degree around, which should remind you of C is smaller or equal than the radical, just that I flanked it with a degree because I want to compare polynomials. Here's another calculation, very similar. The only thing I changed, and of course I have the same typo down here, the only thing I changed is I have higher powers in A now, and as you can see, you get rid of them. For the radical, you do the same count. 1, 1, 1, 8 is 11, and the C itself is 8. So again, this this ABC for polynomials holds. And you could play around a little bit more, and it's impossible to find counterexamples, and that's exactly the statement. So the statement is then for coprime polynomials in this funny field. Actually, you can use any field. You just have to modify the statement a little bit. As usual, links to everything is in the description, in particular to a slick proof. So anyway, coprime polynomials with the extra assumption that they're not all constant, whatever, and the radical is exactly the distinct irreducible factors, the distinct prime factors, and then this always holds, right? It's exactly the same up to that I flank it with a degree. And the most important part is now it's always true. And before you had those funny counter examples, or whatever you want to call them, those funny exceptional examples. That's maybe what you should call them. So here it's just always true, which is actually very, very surprising. I think. Well, actually, the bound I give you is not even sharp. You can make it really sharp by just subtracting 1. And you have a sharp bound. I give you an example here why this is a sharp bound. And the point of this theorem, well, you can formulate it. There are various versions of it. Very nice, very well known. Anyway, the proof itself, linked in the description, not the original proof, but at least a slick proof, linked in the description, is about half a page long. It's also on Wikipedia, so it can't be that bad. It's really, really easy. It's very, very smart. That easy does not mean that it couldn't be smart. It's just extremely smart. It's so smart that it's easy and easy to read. And as far as I know, it was done by someone, Noah Snyder, who was a high school student when they did prove this theorem. Link is in the description to the original short paper. It's only roughly 1.5 pages, maybe 2 pages long. And the proof itself fits on half page, which is in this stark contrast to the ABC conjecture, which, as in 2021, it's not quite settled as far as I understand whether there is a proposed proof, very long. As far as I understand, some people believe it. As far as I understand, some people don't believe it, which should already tell you that it's not completely trivial. As I said, I don't want to take any position here, but compared to a half-page proof, a 500-page proof where it's not really clear whether it's true or not, well, which one is easier? I go with the half-a-page proof. And it's still the same statement. It's almost the same statement, just about polynomials, right? You throw in polynomials, and your ABC conjecture becomes an ABC theorem very easily, not very hard. And that's what I like about the theorem. It's just amazing. I mean, and this one is older than the ABC conjecture, actually. So a little bit older. It's from the 80s, beginning of the 80s-ish. As such as the ABC conjecture itself is also from the beginning of the 80s-ish, but this is a few years younger, older than the ABC conjecture. And of course, you also have Fermat in polynomials, right? Fermat's last theorem, ridiculously hard to prove. Fermat's last theorem in polynomials, very easy, just a consequence of this half-page proof on maybe another half a page, link is in the description, but compared to, well, the proof of the known proofs of Fermat's last theorem, it's just much easier. And it's really just the same statement. You take the Fermat curve, and now you just say there are no whatever QT rational points, and you can vary your field again if you want the stronger statements of this version and everything. It's really cute. And now it really directly follows from the polynomial ABC on, as I said, roughly half a page with a link in the description. This was a huge raffle in particular in the beginning. In the end, I hope it was fairly okay. So you have this ABC conjecture, undoubtedly one of the most important conjectures in number theory, maybe even one of the most important conjectures in mathematics altogether. And yeah, it's hard. It's not easy because you have this kind of funny exceptional cases. And the whole conjecture is actually about those exceptional cases because the proposed inequality doesn't hold. It just almost always holds. Do the same for polynomials. The statement, now exceptions all go away, it is true and is relatively easy to prove. Has applications to a version of Vermaslast theorem, which again on the number theoretical side is, let's say, a bit tricky to prove, and on the polynomial side, it's actually not very hard. Anyway, I hope you forgive me for ruffling so much, and I also hope you enjoyed the video, and of course, I also hope to see you next time.